reports I hear. Who knows? How do you measure such thing? Anyhow, we just watched the Apple keynote 1983, 1984 ad introduction video on YouTube. And the reason I wanted to show that is because maybe not everybody knows that Apple used to have this commercial, or that they made this commercial in 1983 to introduce the Macintosh. And it was like Ridley Scott. They paid this famous director a ton of money. I think it was Ridley Scott to make this ad. And I don't know, shows some sort of paranoia on Steve Jobs' part, I think. But there's also like a weird prescience, or
it aired at the Super Bowl. It's the only time it's ever been
aired. Played at the Super Bowl. But anyhow, it's all about Big Brother in 1984. And so we're going to talk about encryption. And one of the reasons you might want to encrypt stuff is because you don't want, nation states, corporations looking in at your information. And George Orwell wrote that book, 1984, which is all about, Big Brother controlling things and watching people. And it's for your own good. And they had all those interesting euphemisms, like, the citizens for national security, or citizens for the enforcement of peaceful activity. And they'd show up with bats, right?
How many people have actually read it?
Yeah, nobody's read it. How many people have actually read it? I read it at some point, probably.
I read the other book. What's it called?
I don't know.
There's another book.
Christine Cujo?
That's like analogous to this book almost.
Was it Aldous Huxley? Brave New World, yeah. So that's maybe you don't want corporations and big government looking in on all your information, or maybe you're a terrorist and you want to plan your activities and you don't want corporations, big governments watching what you're doing because you want to come and attack them. So the way you do that is with encryption, and that's my intro for encryption. And so here we're going to take a look at building encryption. And so here's the beginning, or here's the end. Sorry, here's the end. Right, where we're taking that same thing, that secret message, and we're doing the same thing. If you look at our routes, we submit a message and then we show the message. Okay, same thing. And we have the right here handle index, and we also have handle message. But we've added in encrypt and decrypt, those two functions. So we've added in the encrypt and we've added in decrypt. And so we're going to take our message when it gets sent in, and we're going to encrypt it, and then we're going to take our message when we want to show it, and we're going to decrypt it. And here's what that kind of starts to look like to do some encryption and decryption. So there's all kinds of options when you want to encrypt things. There's a bunch of different packages out there that you could use. But the basic idea for encryption is what? How does encryption work? What are you doing?
Kind of secret key that's only available to the encryptor and decryptor?
Yeah, so if you want to encrypt something, you're going to take what you want to encrypt, and you're going to run it through some sort of processing, and it's going to make it all jumbled. It's encrypted. And if you want to decrypt it, you're going to run it through some sort of processing again, and it'll unjumble it. All right, so that's the basics of encryption. Take something, jumble it, and then take that jumble and unjumble it. Right? Well, how are we going to jumble things? Let's just talk, don't look at the code, but let's just talk in general. How do you jumble things? Like, what's really basic encryption would just be like Caesar cipher, rotate 13, rot 13, where every letter of the alphabet gets rotated. We looked at that earlier in the semester. You guys remember? So something that's a little bit more complex is we have some sort of a key that's required to pass into the jumbler, right? The function that jumbles it. And with that key, it'll jumble it in a certain way, and then to unjumble it, you need that key so it could be unjumbled correctly. So based upon that key, it runs some functionality, and it's able to unjumble it, right? So that's the idea of encryption, jumbling and unjumbling. Those are my words. Encrypting and unencrypting, decrypting. And so there's a lot of packages out there. If we go and look at godoc.org, and look at crypto. All right, so here's package crypto, but we go down to the bottom, and there's all these different directories. So we have AES, implements AES encryption as defined in US. Cipher, all these different ones. HMAC, which we kind of talked about a little bit with cookies. MD5, there's a RAND package. Here's SHA-1, SHA-256. They're subtle. Package subtle is, you know, Caleb Doxey's favorite name for a package because it's very subtle. and it takes a lot, implements functions that are useful but require careful thought to use correctly. And so one of the things I think in subtle is to make the amount of time constant. So if somebody is trying to, you know, hack your stuff, one of the ways they could hack that is by, what's it called? It's a side channel, I think, side channel attacks. So side channel attack, right, is where you're looking at the processing, right? And so it's a side channel attack is any attack based on information gained from the physical implementation of the crypto system, rather than brute force or theoretical weaknesses in algorithms. For example, timing information, power consumption, electromagnetic leaks, or even sound can provide an extra source of information which can be exploited to break the system. An attempt to decode RSA key bits using power analysis. What? Right? They're looking at how much power is consumed. So one of them is like here, timing information. And so each time you try, like if you're trying a password against another password, maybe one attempt would take longer to match than another attempt. And so you could start to figure out, well, that one took, you know, 2 nanoseconds more. So that probably meant the first characters matched or didn't match, right? Anyhow, so package subtle makes time constant, so you can't do that side channel attack. So there are these packages, and then there's also, where would I find it? It is Golang.org x Crypto. How do I get there? I think maybe if I just enter Google. X OAuth, Golang.org x OAuth 2. Right, so if I just go to Golang.org OAuth and then, I just want Golang.org x. Does that give me anything? Not found. Golang.org, Golang.org. Not found. So I got to know the X, OAuth, crypto. So where's the whole list? Index? That's just that index. Crypto. That takes me to GitHub. Golang.org, Golang.org, X. That's just interesting to me. Like, where do I see all of the X ones? Because I want to find that. So I don't get to see it here. These are all the crypto ones, but there's more to that, right? Like we saw that one of the ones there is OAuth. And so there's that OAuth, right? So here are the OAuth ones. So let's go to Golang.org and /X. Isn't that what it is? Golang.org /X. And so here we go. Perfect. So here we have blog, crypto, and one of them was OAuth, wasn't it? Golang.org OAuth 2. But maybe, So that's just like interesting. So packages, OAuth 2. So here is auth, and then down here, OAuth 2. So all this stuff, Go subrepository packages. These packages are part of the Go project, but outside the main Go tree, so the main SDK. They are developed under looser compatibility requirements than the Go standard library, the Go core. So it's stuff Google might use internally, or it's things that might be making their way to the standard library. But this is all Google written code, but looser compatibility requirements. So, you know, the one we're looking at now is crypto and NaCl. Okay? And here, NaCl. Secret box. Why is it called NaCl? NaCl is sodium chloride, and sodium chloride is salt. And with cryptography, you often salt things. All right, you add a little piece of information into the jumbler so that it jumbles in a certain way. or you salt like a random number or something like that. I don't totally understand cryptography. It's new territory for me. So if I say things incorrectly, or if you're watching this online, you should know that I'm no expert. All right. So here's how it works. And the easiest way to understand it is kind of break it out in pieces. And so one of the things we want to do is we're going to, this is to encrypt, and to encrypt, we are going to do secret box seal. And so what is secret box? So here we're at NaCl secret box, right? So it's a secret box. So this abstracts, and this was explained to me by Caleb Doxey at the summer boot camp, and Caleb's awesome. He's the author of golangbook.com. But secret box abstracts a lot of the cryptography, so it makes it easy to use, right? Meaning they do a lot of the complicated stuff in the background for us. And so we have here in the index, we have open. So we could open a secret box and we could seal a secret box. So sealing is encrypting. Put it in there and seal it. Opening would be decrypting. Pull out what's in there and let me see it. Okay? And so how does sealing something work? And you can see that that's right here where when we encrypt, we're going to seal something. So here is sealing. Seal appends an encrypted and authenticated copy of message to out. Right there. Encrypted and authenticated copy of message to out, and which must not overlap message. The key and notes pair must be unique for each distinct message. Key and notes. And the output will be overhead bytes longer than message. Crazy, right? Like you read that and you're like, I don't know what the heck that means. At least I do. I read that and I'm like, what? New information. Well, how do we actually use it? So we're just going to say nil here, because this will return a slice of byte. Well, we don't need to append to out. To hell with appending to out. We're just going to get our slice of byte back and store it here, because it returns a slice of byte. And then so to nil on that out thing, and then right here we need a notes. What is a notes?
Nonce.
I'm not saying it right. Nonce.
One-time word.
So it's a number you're going to use one time. Why would we want to use it one time?
Encrypting something. Okay.
We are in a self-destructing message 02, 04. This will give somebody access to get it, right? So if they go to, this URL and paste in that key, they will have access to the message. But right now, this is the message. That's what's stored there. If I was to go look in App Engine, at memcache, paste in that key, the value I get back is that crazy encryption, hexadecimal encryption. There's a colon right there. Here's my notes. When I do the encryption, when I seal my secret box, I'm giving it that notes. So secret box seal takes nil on that message and then the notes. So nil on that message, and then the notes. So I'm passing in that secret, I'm passing in that notes, that number to be used one time. And then when I decrypt it, so secret box open, I have to give it that number again. And this is actually clearer on this file. So here's the decrypt, right? And I'm getting the notes from that string. So I'm decoding that string from hexadecimal, right? Hex decode, getting a byte slice. And then I'm copying from that byte slice into notes, 24 bytes, right? And that turns it into a slice with an underlying array, because this is an array. So I copy that byte slice here when I decode that. And the part I'm decoding is parts. And parts comes from splitting that hex string on a colon and giving me 2 parts. And I want the thing at item position 0. So right here, I'm splitting on that. I'm getting this thing, right? And then I could pass that in and decode it. So what is the point of that, Kai?
The point of the nonce, the point of what?
The nonce. Why is this appended to, right? Like, there's my encrypted message. It's got 2 parts. Why do I have that there?
Because you're going to need it to decrypt.
Yeah, but why include it in the string? If somebody got access to the string already and they want to decrypt it, they got that part.
Oh, yeah, good point.
And they could just stick it in. Oh, okay, this is secret box. Let me stick that in.
Do they need, or do they need the key too? Or that is the key?
And they also need the password to open the box. So they need those 2 pieces. But they just got one of the pieces here. So why even include that piece?
It's a one-time use, and the receiver of the message doesn't have it. Because he generated it when he made the message, right?
It's a one-time use.
And it was generated when the message was made.
Generated when the message was made.
So the person receiving the message doesn't have it yet. Until you have to give it to them.
I have to give it to them. But I'm also giving them the password.
Well, do they know the password ahead of time? I mean, is that something you've already shared with them?
To decrypt it, right, I need those 2 pieces. So the reason that's there is, and let me look at my Google history. Dangerous, I know. Screw it, I don't want to sign in again. So it's it prevents like if somebody else, right? Like if Bob and I are communicating, and then Carson grabbed the communication, and then Bob has already redeemed the message, and then Carson comes and tries to redeem the message also. You know, like if Carson has, you know, if Bob and I are communicating, and this is getting decrypted, and here's the password, and then Carson gets it, right? Intercepts the communication. Well, he has this, right? But the next time it's going to be different. So he can't come back and, you know, next time, like with the next thing, be the one to unencrypt, because this is going to be different next time. Every time that's different. So it's just something that every time it's different. And I'll look up what that is.
But
Yeah.
for someone to intercept it, they have to get it before it's been opened first.
Yeah, because it's self-destructing. I don't know. It's a trip, man. I wish I could find the wiki. All right, I'm gonna look it up. Google search history.
Wondering why it would or wouldn't matter if the attacker got the dots.
All right, so here it is. It's a replay attack or a playback attack. Valid transmission is maliciously or fraudulently repeated or delayed. This is carried out either by the originator or by an adversary who intercepts the data and retransmits it, possibly as a masquerade attack or IP packet substitution, such as stream cipher attack. So here's the example. Suppose Alice wants to prove her identity to Bob. Bob requests her password, which Alice provides. Meanwhile, Eve is eavesdropping and keeps the password. After the interchange is over, Eve connects to Bob. When asked for proof of identity, Eve sends Alice's password, read from the last session, which Bob accepts as granting access to Eve. Okay? A way to avoid this is to use tokens, session tokens. Bob sends a one-time token to Alice, which Alice uses to transform the password and send the result to Bob. On his side, Bob performs the same computation. If and only if both values match, the login is successful. Now suppose Eve has captured this value and tries to use it. Bob sends a different session token, and when Eve replies with the captured value, it will be different from Bob's computation. I know crypto is like that, right? So that's what that little deal is doing. All right, so let's look at it just from the beginning. So here we have creating our nonce. Nunts. 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 Nonce. Nunts. This is nuts. No, once.
Yeah, that's what
Nuts.
I was
Nuts.
thinking.
Once, nuts, nuts. All right, so Control C. All right, pa-bow. So that's what that code does right there. What is this? What is that type? Slice a byte? How many people agree with Bob? Raise your hand. What is it?
It's a 24.
When you see a number in between the brackets, it means what and go. It's not a slice, it's an array. It's array of byte, and the length is 24. Okay? And so there we have array of byte, length is 24. And when we print it, we see this. So everything is 0 valued. Right? And a byte is what? What is a byte? A byte is an alias for which numeric type? A byte is 8 bits, right? UN8. 8 bits, man. 0 to 255. Because if you have 8 bits, you can store 256 messages. 2 to the power of 8. 2 times 2 times 2 times 2 times 2 times 2, whatever, is 256. 2, 4, 8, 16, 32, 64, 128, 256. We don't go to 256 because we start at 0, so it's 0 to 255, not 1 to 256. It's 8 zeros and ones. What would that number be? I just messed that up. What would that number be in decimal? Who knows, right? Here's our ones place, our twos, our fours, our eights, 16, 32, 64, 128. Is that right?
Okay, so that's 128.
Ones,
32 plus 1 plus 7.
7.
2, So 1, 2, 4, 8, 16, 32, 64, 128. 128 plus,
37.
yeah, right, who knows. Anyhow, it's 8 bits.
165.
A byte is 8 bits, or that's a byte, 8 bits. And so we print that, we get the zeros, and then we use read at least, rand reader, nonce, 24. What the heck? How can we understand that? Where would you start? Let's start with read at least. What's read at least? Read at least is from package.io, so we could go look it up in package.io, but we could also just do here. Read at least reads from R into buff until it has read at least minimum bytes. So read at least reads from R into buff until it has read at least minimum bytes. So read at least reads from R into buff until it has read at least minimum bytes. Interesting. It returns the number of bytes copied and an error if fewer bytes were read. Right? And blah, 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 other stuff, okay? So reader, buff, and it's a slice of bytes. Buff is a slice of bytes. That's what buff is. It's a slice of bytes. They're just calling it buff. It's like a buffer where you're putting stuff. The buffer is a place where you could stick stuff. So what I have here, do I have a slice of bytes? It's an array. How do I take an array and turn it into a slice? Conversion might be one way, but this is I slice it. I could slice the array, and it becomes a slice. And what is a slice? Is it a built-in type, or is it a composite aggregate type, or is it a reference type, or some combination of all of that? A slice, a map, and a channel are all what? Reference types. What is a slice referencing?
A location to an array that's
Yes,
undefined and
yes,
size.
and a location to an array.
That's undefined in size.
So when we do this, we create a slice, right? We are slicing this array. So we're slicing that array, and we're doing it right there. That's the slicing. That creates a slice, which is now pointing to the underlying array. So we got a slice of byte pointing to that underlying array. So as we store values into that slice, they're going into the underlying array, which is our once, in once, right? So that's that, and then we need the 24 is the minimum number, so put in 24 here. That's how many we want in there, because that's the size of our array. And then we have rand reader. Well, what is rand reader? This is from package rand. And reader is a global shared instance of a cryptographically strong pseudonym random generator. Huh. Right? It's a variable. And a global shared instance of a cryptographically strong pseudo-random generator. Interesting. Right? If you're on Unix, it reads from dev urandom. Linux reads from that. Windows reads from this. So right here, in an implement, it's of type IO reader. So here we could do that. I don't totally understand this. This is code from Caleb, but I kind of understand it. It's a reader. This asks for a reader, right? This is a slice of byte. Asks for a number. Okay. And when we run that, right, it generates random numbers and puts them into our array. Thanks, Bob. Nonce.
No.
So that's what that first part does. Here's what the next part does for encrypting. Let's just run it and see.
Only use the nuts once again.
All right. So we get a message, and that's not encrypted. Just want it to be on the same screen. Cool. We get a message that's not encrypted, and then we do var nonce and read release. We put a bunch of random numbers in there, and then we do the same thing with the password, right? And so right now we're looking at file 2 encrypt. So we got, you know, our nonce, and then we have our password, and then we encrypt it secret sil and nil, and we give it a slice of bytes. So we give it our message, right? So there's our message. And we give it our nonce and our password, so that's what, you know, secret box seal uses to jumble it all up. And that gives us the encrypted value. So when I print the decrypted value, I get this, right? And then when I print the encrypted value, the first thing here I print is just what's the encrypted value. It's this, right there. And then I thought, well, what's its length? 61. And what happens if I turn it into a string? I get this craziness. And then what happens if I just print the nonce? I get this. And what's the difference between printing the nonce and printing the nonce after slicing it? Same thing. And then what is the encrypted value? And the nonce in hexadecimal. And so here is the nonce in hexadecimal all the way to the colon. And then here's the encrypted value in hexadecimal. Kind of interesting, it included encrypt 02. Oh, crap, that's nuts. Here, I gotta do this. And then rerun it. So now, what I was looking at is just the next prompt. So that encrypted it. Yay! Let's decrypt it. But before we do that, I want to take out those returns I put in. So here's the encryption again up at the top. But, you know, with a lot of the printing and stuff taken out. And so I take my encrypted value and then I string print it this time into just encrypted hex. And so there's my encrypted hex. And then down here, I'm going to decrypt it. So to decrypt it, I'm getting another nonce. Just I called it nonce 2 to let you know it's different. And I'm splitting my string, my encrypted string, by the colon. So I have my nonce part in the first position and the message, encrypted message, in the second position. And then I'm going to get the nonce. So I'm going to decode my hex, and give me what's in parts, right? That's what I got when I split up my string. Give me what's in the first position, so at index position 0. And decode that and give it to me in my byte slice. So I just got my nonce as a byte slice, and I'm going to copy my nonce into that array, right? But this is a byte slice, so I need to copy it into a slice, so I need that to turn this nonce 2 into a slice. So this is the destination, this is the source. And then I do decode string, and the second thing is the message, which is encrypted as hex. So I'm going to decode that hex into a byte slice. So this is still totally jumbled. I haven't unencrypted it yet. But now I'm going to open that. I'm going to pass in that byte slice, give it the nonce, and give it the password. Right? So the password, you know, is always the same, but every time the nonce is changing. And so, you know, if somebody then, you know, the message was there, you know, if they captured all that information and broke it, right, then the next time the nonce would be different. It's just, I can't get my head totally around that. I got to figure that one out. But anyhow, this opens it, so I get my message, and then I print my message. So there's my message. So print it out, and when I run that, not that one. So before encryption, some message that you want to store securely, encrypted, and then after decrypting, some message that you want to store or send securely. That's pretty amazing. So this code right here, you could build that Proton Mail website with encrypted email. You could stand up a server and offer anybody in the world completely encrypted messages. That's really interesting. I mean, pretty powerful. Like if you just had a website, it's like encrypt any message and send this URL to somebody, and then somehow send them the password, or with that URL, they could then open it, right? And so you could break up the pieces, right? Like so they could reconstruct it. I don't know.
You could also do something like PGP and just store the keys in your database on Google and use authentication on top of that. Make it a regular email service with hash passwords, and on top of that, encrypt emails and let people have private keys and stuff on your server. Anyway.
Yeah, that's one of the things I am interested in learning more about. So there's Udemy, which is one place you can learn about stuff, right? And then there's Pluralsight, and then there's Udacity, and then there's Udemy, Pluralsight, Udacity, Coursera. And so if we just looked here, cryptography, 5 hours of video. Looks pretty cool. Or Pluralsight. That'd probably be pretty good. This is like only 2 hours long. Or Udacity. We got a lot of courses now. Security. OAuth. Or here, cryptography. Whoa. University of Maryland, Stanford University, those would be awesome. Can you imagine? What language?
I think I actually signed up for the Stanford one before, and they were straight up demonstrating math on the whiteboard, but really close, like the projector was right over the whiteboard. And I was like, geez, I don't have the patience, because I was already enrolled in all the computer classes.
The other one that looks really good to me at Coursera is algorithms. These two right here, Princeton Algorithms Part 1 and 2. Anyhow.